Let us consider an example of this. Say we have an aluminum rod where our modulus of elasticity is given as 69.0 gigapascal and our outside diameter is given as 100 millimeters. And this aluminum rod is inserted into a steel tube. Now the steel tube has an inside diameter of 100 millimeters and outside diameter of 150 millimeters. The modulus of elasticity of our steel is given as 200.0 gigapascal. Both the rod and tube have a length of 500 millimeters. If an applied load of 1000 kilonewtons is applied to the rigid plate B, we want to determine the deflection of the rod-tube system. Now, for us to begin, step 1 requires us to draw a free body diagram of the system. And if we draw a free body diagram, we must cut our rod-tube system to determine our internal reactionary forces. Our internal reactionary forces are denoted RS, i.e. the internal reactionary force of the steel, and RAL, i.e. the internal reactionary force of the aluminum. And from our equilibrium equations in our x direction, we have RS plus RAL is equal to minus 1000 kilonewtons. We recognize that this is a statically indeterminate problem. Thus, we have to employ a deformation equation that's going to relate our internal reactionary forces to that of support A, which is expressed in terms of our applied load. Step 2 is for us to draw a displacement diagram. We see our rigid plate is going to displace from B to B prime, and the deformation of our steel and aluminum are going to be equal. That is, we can say delta S is equal to delta AL. This is going to be our compatibility equation. Step 3 requires us to substitute in the variables from our equilibrium equations into our deformation equations that we developed from our displacement diagram. From our displacement diagram, we had the deformation of our steel being equal to the deformation of our aluminum. The deformation of our steel is given as RS times LS per ES times AS. This is equal to the deformation of the aluminum, which is given as RAL times LAL per EAL times AAL. Thus, we can say our deformation equation is as follows. The deformation of our steel is given as RS times the length of the steel, which is 0.500 meters, per the elastic modulus of our steel, which is given as 200.0 gigapascal, times the cross-sectional area of the steel, which is given as 9.82 times 10⁻³ meters squared. And this has to be equal to the deformation of our aluminum, which is given as RAL times the length of 0.500 meters, per the elastic modulus of our aluminum, 69.0 gigapascal, times the cross-sectional area, 7.85 times 10⁻³ meters squared. Now, in this equation, we have two unknowns, but we recall from our equilibrium equation, we also have two unknowns. Thus, with two equations and two unknowns, we can solve for the internal reactionary forces RS and RAL. We'll put these equations in matrix form. Thus, we can see our first matrix is the coefficient matrix, which is the coefficients of our reactionary force of the steel and aluminum from our two equations. The first row of our coefficient matrix gives the coefficients for RS and RAL via our equilibrium equation, which on the right-hand side, we see the first entry is minus 1000 kilonewtons. Now, in the second row, we have the coefficients for RS and RAL from our compatibility equation, i.e. our deformation equation, and this is equal to 0. Now, using matrix inversion, we can solve for our reactionary force of the aluminum and steel. We find that the reactionary force of the aluminum is minus 217 kilonewtons, and that of the steel is minus 784 kilonewtons. As a check, we can add these two together, and within the uncertainty of our given applied load, we see that this will match our original equilibrium equation. Lastly, we can calculate the deflection of the plate via the deflection of the aluminum or steel. The deflection of the steel is RS LS per ES times AS, or minus 784 kilonewtons times 0.500 meters per 200.0 gigapascal times 9.82 times 10⁻³ meters squared. And this is equal to minus 2.00 times 10⁻⁴ meters. As a check, we can calculate the deformation of the aluminum, which is RAL times LAL per EAL times AAL. And we have minus 217 kilonewtons times 0.500 meters per 69.0 gigapascals times 78.5 times 10⁻³ meters squared. And we find the deflection of the aluminum is also equal to minus 2.00 times 10⁻⁴ meters. These two deformations are equal, which verifies our compatibility equation.